Hello friends, today I am going to teach about the Leibnitz Theorem. So let's begin the video. First we write the statement of this theorem. I have already written the statement of this theorem, which is as the statement of this theorem says that let u and v are two functions of x such that the u and v are the nth time differentiable. That means we can differentiate both the function u and v nth times. We represent the nth derivative of u by un, n is in the suffix. Similarly, we represent the nth derivative of v by vn. Then the theorem says that the nth time differentiate of u into v, that means nth derivative of the product u and v will be equal to un into v plus nc1 into un minus 1 into v1 plus nc2 into un minus 2 into v2 plus dot 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 in the last term ncn into u into vn. So this is our statement of Leibniz theorem. Now we are going to prove the theorem. Before proving the theorem, we write here the three formulas that will be used in the proof. The first formula is the general form of combination NCR, and NCR will be equal to the factorial n upon n minus r factorial into factorial of r. The second formula is that NCn and NC0 both will be equal to 1. NCn equal to NC0 will be equal to 1. And the third formula is that NCr minus 1 plus NCr will be equal to n plus 1 Cr. So these are the three formulas that will be used in the proof. So we have to remember these formulas. So now we are going to prove the theorem. We will prove this theorem by the method of induction. What is the method of induction? We know the process of induction method. First we will prove the theorem is true for n equal to 1. This n we will put n equal to 1. So we will prove uv1 is in the form of this type. That means uv1 satisfies this equation. After that we will prove uv2, that means the second derivative of the product uv satisfies this equation. Similarly, we will prove uv3 also satisfies this theorem, and after that in the second step we will assume that for n equal to m this theorem is true. This theorem is true. That means we will assume that uvm satisfies this equation, and after assuming this result we prove that this theorem is also true for n equal to m plus 1. Then the theorem is proved. First we prove that uv1, uv2 and uv3 satisfies this theorem, and after that we will assume that for n equal to m this theorem is true. Then if we able to prove that this theorem is also true for n equal to m plus 1, then we are done. First we will prove this. We have to differentiate UV first time. So we know the process of differentiating any product form of two functions. We will write here u1v plus uv1. We differentiate the first term and we write the second term without changing anything, plus we write the first term without changing anything, and again we differentiate first times the second term, which is equal to v1. So this is our process of differentiating any product form of two functions first time. Again we differentiate this second time, that is to get this. We again do the same process as we have done in the above. So we differentiate u and v. To differentiate we will write u2v plus u1 v1, plus again we differentiate u v1. So we will obtain here u1 v1 plus u v2, but we note that these two terms are equal, so we will write these two terms in one place. So it will be equal to u2 v1 u2v plus 2 of u1 v1 plus u v2. Now to get these values in the form of our required result, we will write 2 as 2c1, 2c1, u1 v1 u v2. So clearly this is the form of our given or required result. Now we will prove this result uv3. For uv3 we again do the same process. We differentiate first this term, again this term, and after that this term. So differentiate this term first time, we will get u3v plus u2 v1, and there is no changing this constant, it will be as 2c1, and we differentiate this term the first time to get u2 v1 plus u1 v2. Again we differentiate this term to get u1 v2 u v3. We did the same process, like we differentiate first u the first term first times, then we get u1 and we write the v2 without changing anything, plus we write the first term without changing anything u, and we write into the first derivative of v2, which is equal to v3. Now here also the terms are equals and these two terms are equal, so we write these equal terms in the one place. Then we get u3 v1, this is the value, means 2c1 equal to 2, and the coefficient of this term is 1, so this will be equal to 3 u2 v1. Here 2 u2 v1 plus 1 u2 v1, so we will get 3 u2 v1. Similarly here 2 u1 v2 plus 1 u1 v2, so we will get 3 u1 v2, and the last term u v3. Now to write these values in the form of our required result, we can write it as u3v plus 3c1, as we know that 3c1 is equal to 3, u2 v1, and we can also know that 3 is equal to 3c2, and u1 v2 plus u B3. We can prove here that 3C2 is equal to 1. 3C2 by formula it is equal to this factorial 3, factorial 1 and factorial 2. This will be equal to 3. Now we have obtained all these three result as in the form of our required theorem. This UB2, this and this. So the theorem is true for n equal to 1, n equal to 2 and n equal to 3. Now we are going to assuming that this theorem is also true for n equal to any arbitrary number m. Then if we are able to prove the theorem is also true for n equal to m plus 1, then we are done with our proof. Let the theorem is true for n equal to m. Then we will obtain as u into v m, that is mth time derivative of the product ub will be equal to, as done previously, it will be equal to um v plus mc1 um minus 1 v1 plus mc2 minus 2 v2 plus dot dot dot. The last term we will be equal to mcm vm. We can note here that we will write minus 1 and m minus 1 is obtained from subtracting these two numbers m minus 1, and this one is obtained by this term 1. Similarly here m minus 2 is obtained by subtracting these two numbers m minus 2, and this term 2 comes from this number 2. Similarly here it is 0, so m minus m equal to 0, and this number m comes from this number m. Now we are going to prove the theorem is also true for n equal to m plus 1. To obtain uv m plus 1, what we have to do? We have to do only the differentiate these result the first time to get uv m plus 1. So we will do the differentiation as we have done above. So differentiating this term we will get um plus 1 b plus b1. Here we done that we done the first derivative of this term to get plus 1 into b without changing anything, plus we write the first term without changing anything into we derive the first times the second term b to get b1. Similarly we will write here mc1 and we differentiate this term the first time. Then we will obtain that um b1 plus minus 1 b2. Again we write this term, the first derivative of this term. Then we will get mc2 minus 1 b2 plus minus 2 b of 3. Again we differentiate the first term that is minus 2, first time derivative of this term will be equal to m minus 1 and we write v2 without changing anything, and plus we write m minus 2 without changing anything, and we differentiate first time v2 which is equal to b of 3, plus dot 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 we differentiate the last term, and this will be equal to mcm u1 bm plus u bm plus 1. Now we will observe from here that these two terms are equal. Similarly, these two terms are equal. So by hypothesis, this term will be equal to any term, and also this term will be equal to any of term here. So we will write the equal terms in one place, then we will get u v m plus 1 as u m plus 1 b, this term, and we will write these two terms in one place to get um v1, and as the coefficient of this term is 1, so we can write 1 as mc0. And what is the coefficient of this term? It is mc1. Plus we take this term as common, um minus 1 v2, then what is the coefficient of this term? It is mc1, and the coefficient of this term is mc2, plus dot dot, as this term is taken common, so we will not write this term and we only write this last term, which is equal to mcm u bm plus 1. Now we saw a proof or a formula here that ncr minus 1 plus ncr is equal to n plus 1 cr, means that we take here n as n plus 1, that means we add 1 in this number n, and we write the maximum of this number. What is the maximum of this number? R minus 1 or R? Absolutely R, so we write n plus 1 cr. So we will use this theorem there in these terms. So it will be equal to u m plus 1 v plus u m v1, this will be equal to m plus 1 c1 plus u m minus 1 v2, this will be equal to m plus 1 c, and the maximum of these numbers 1 and 2, which is equal to 2, plus dot dot dot, we can write mc1 as m plus 1 c m plus 1, as the formula says that ncn plus or ncn is equal to nc0 will be equal to 1. So if we take these numbers same, that means n equal to n, or we take any variable alike here, means equal here, then this will be equal to 1, and any number here taken n or m, any variable, and if we take n c0, then this will be equal to 1. So here nc1 value is 1 and this value is again 1, so we can take mcm as m plus 1 c m plus 1, because these two values are equal to 1. This term we will write here. Now this is equal to u v m plus 1. Now we will observe this result satisfies this format or not. That means, is this theorem is true for m plus 1 if this is true for m by induction method. So we can see that if we take mth time derivative, then this will be equal to this form, and we will get here that if we take m plus 1, then we will obtain here this form. Is both the form are equal or not? This is our task to watch. Now we can see from here that if we take mth derivative of uv, then it will be equal to umv. Here if we take m plus 1 times of derivative of product uv, then we will get um plus 1v. So in the place of m, we will obtain here m plus 1. Similarly, in the place of mc1, we will obtain here m plus 1 c1 into umv1 plus mc2. In the place of mc2, we will get here m plus 1 c2. So, and in the last term, here it is mcm uvm, and in the format of uvm plus 1, we will get here m plus 1 cm plus 1 uvm plus 1. So clearly both the format are alike. So we can say that the theorem is true for n equal to m plus 1 also. So by induction theorem, we are done with our proof. We can write here as the theorem is true for n equal to m whenever the theorem is true, the theorem is true for n equal to m, where m is arbitrary. As theorem is true for n equal to m whenever the theorem is true for m equal to m, where m is arbitrary. But it is also true for n equal to 1, 2 and 3. So by induction method, we can say that consequently the theorem has been proved. Thus in this way we are done with our proof of Leibnitz theorem. Now we take an example to understand the use of Leibnitz theorem. So example says that we have to derive nth time derivative of the product x multiplied by e to the power x, where e to the power x is exponential of x. So basically the Leibniz theorem, by Leibniz theorem we can obtain the nth derivative of any product of two functions together. Now we are going to derive the nth derivative of this product. Let we take u as e to the power x, u as e to the power x and b as x. Now we differentiate u and v both the nth times. So un will be equal to ex. But we know that the derivative of ex is ex. Similarly, we can see here that u2 will be also equal to e to the power x. That means if we differentiate again ex, then we will get also ex again. Similarly, also in the nth time we will obtain the derivative of this as this. Now we derive the v1. If we differentiate the term x, then we will get 1. Again we differentiate 1, as this is a constant, so we will get 0. So in this way we will obtain any higher derivative as 0. Now by theorem, Leibnitz theorem, gives us u into v n. That means nth time derivative of u and v is un v nc1 u n minus 1 v1 plus nc2 u n minus 2 v2 plus dot 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 ncn u into vn. This is our formula. So we have to put now these values in this equation. Un, what is un? Un is ex. V, what is v? It is x. nc1, it is equal to n. u n minus 1, u n minus 1 is also e to the power x. v1 is 1. nc2 u n minus 2, it is also e to the power x. v2, it is 0. And in the next term this will be 0 plus 0, as here v3 comes, again v4 will come. So we know that these values are all 0, so all the values are equal to zeros. Now we will write again ex into x and e to the power x plus 0. So this will be equal to uvn, u is equal to ex into x, and that means nth time derivative of ex into x will be equal to, if we take ex as common, then it will get like this. So this is our result. That means nth time derivative of the product ex into x will be equal to e to the power x plus n. So this is an example of Leibnitz theorem. So I hope you understood the theorem, Leibnitz theorem. If you like my videos, so please like and subscribe my channel. So that's it for today. Thank you.